So we are moving into Chapter 8. We're going to be lesson 8.1 today, which is called the multiplication counting principle. Chapter 8, we're going to really be diving into powers and roots and dealing with exponents and all the different things that can happen when we multiply and divide, add and subtract powers or things with exponents. There's lots of different rules, things that you've dabbled in before in Math 8, maybe a little bit in Math 7, but mostly Math 8. We're going to talk about scientific notation. We're going to talk about different ways of expressing numbers using exponents. And so today we're going to dive right in. The big idea, expressions involving powers, so exponents, result from certain counting problems. That's what we're going to look at today. And sometimes are used in scientific notation. So we just did kind of a warm-up to review scientific notation, which is a number expressed by x times 10 to the n, like 3 times 10 to the fourth, where n is an integer, and then, so integer, whole number. Okay, it could be negative, but it's a whole number, not a decimal up here. The power of 10 is a whole number, that's an integer. And then x has to be between 1 and 10. So it can be 1, it can be equal to, and it can't be 10, it's got to be less. So basically it's going to be a single digit number, but it can also be like 1.6 or 6.45, as long as that number is between 1 and 10. So it can be 1 or any number between 1 and 10. And we use them for very large or very small numbers. So the thing we always kind of fall back on when we talk about is if you're measuring distance in space, you're talking about billions and trillions of miles, and you're going to, or not even miles, light years, and you're going to express those in scientific notation. And same thing for really small. If you're trying to measure the size of something in a cell, okay, it's super, super tiny. And so you can't just put a regular number to it. So we're going to use scientific notation to express those really small numbers. All right, so let's jump right in. First thing we're going to talk about is the counting principle and how do you find out how many different possibilities there are in different situations. So example number 1, suppose next year you want to take a foreign language class. You also want to take a math class and an art class. The language classes that are available are French, Spanish, and German. So you're going to have to pick one of those. The math classes are algebra or geometry. You're going to have to pick one of them. And the art class is photography, painting, or ceramics, and you got to pick one of those. How many possible ways could you create your schedule? Okay, so you might say 3 at first, just off the top of your head, 3 different ways, but that's not true. There's 3 different options for just your language class. And then depending on which one of those you choose, there's 2 different math classes. And then once you've chosen your language and your math class, now you have 3 different options for choosing your art class. So let's actually write that down. So your language class, you've got 3 options. Your math class has 2. And your art class has 3. So this falls back kind of on probability. And you want to know how many different ways can you arrange these? How many different schedules can you make? And so all we have to do is take each one of these number of options and multiply them together. That's your counting principle. And that'll tell you how many different possible schedules there are. Now you may have seen these in like a tree form. So your language classes, you could actually set them up. You've got French, you've got Spanish, you've got German. And then from each one of those, you could go either algebra or geometry. Algebra, geometry, algebra, geometry. And then from each one of those, you've got 3 more choices. So 3 here, 3 here, 3 here, 3 here, 3 here, 3 here. So if you look at it, you've got 6 different ways you could get to this point. French and algebra, French and geometry. Spanish and algebra, or Spanish and geometry. German and algebra, or German and geometry. And then down each one of those roads, they could split into another 3 with photography, painting, and ceramics. And so each one of those would branch off. So if you think about it, you have 6 right now. Each one of those are going to branch out by 3. And so that creates 18 total. So this is called a tree diagram. That's one way to go about it. But all we have to do using the counting principle is multiply the number of options in each set, and it's going to give you the total. So 3 times 2 times 3. 3 language options times 2 math options times 3 art options, 18 possible schedules. Okay, and that's your counting principle. So let's try this with example number 2. Radio stations call letters such as W, N, E, W. They must start with a W or a K. So the name of a radio station is going to have 4 letters, and the first one has to be a W or a K, and the rest can be anything. So how many options are there for the first letter? Well, that first one has to be a W or a K. So 2. But how many options are there for the second letter? So the second letter can be anything you want in the alphabet. So how many letters are there in the alphabet? 26. And then you would have the same number for your third. You can pick any letter. So another 26. And then you'd have the same number for your fourth, any 26. So these can repeat. It's not like you have to go down to 25 for your next one and then throw that letter out and now you're down to 24. You can reuse the same letter. So you could have W, N, E, N. So just because you used N as your second one doesn't mean you can't use it as your third or your fourth. So for every single one of these, besides the first one, you have 26 options. So how many different 4-letter names are possible? So for your first letter, you've got 2 options. For your second, we already said, you've got 26 options. For your third letter, so 1, 2, 3, again, have another 26 options. And for your fourth, once again, you still have 26 options. And so using your counting principle, we're just going to multiply the number of options, and that'll tell you the total number. So 2 times 26 times 26 times 26. That's the total number of options. If you wrote down every single combination of letters to create this, that comes out to 35,152 possible radio stations. So there's lots of possibilities. All right, let's flip it over and let's start using some of these things in scientific notation. So example number 3, we're looking at a test. It's got 10 true or false questions, and then it's got 5 multiple choice questions, and those multiple choice questions have 4 choices. So true or false, you think about it, how many different options are there? There's only 2. So when you have a true or false question, you have 2 options, true or false. Now on your multiple choice questions, every test is different, but on this specific one, there's 4 options for each one. So the question says, how many different sets of answers are possible? So you could have the first one be true, the next one be true, the next one be false, the next one be true. And if you went through every single different combination, how many different sets of answers are possible for the entire test? We're going to write this answer in exponential, base 10, and scientific. So exponential is using exponents. Scientific notation we've talked about. It's something times 10 to a power. And base 10 is just a regular number. Okay, expanded number like you would normally see on an everyday basis. So let's start with exponential. If we're going to write this, so first of all, there's 10 true or false questions. So the very first question, how many options are there? 2. Could be true or false. The next question, how many options are there? 2. Could be true or false. The next one, 2, 2, 2. So far we have 5 questions. Each one of these could be true or false. Each one has 2 options. So far we would do 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So if you had 5 questions, there's 32 possibilities of how you would order this: true, false, 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 true, false, true, false, true. Okay, 32 so far. Now this is only 5 questions in. There's 10 true or false questions. So we need another 5. So 1, 2, 3, 4, 5. Now that just handles your true or false questions. You can already see there's a lot of different ways you could order this. And now there's 5 multiple choice questions. So your first multiple choice question, there are 4 possibilities, A, B, C, D most likely. Your next multiple choice question, there's another 4 possibilities. Another 4, another 4, another 4, for a total of 5 questions. So 10 true or false, 2 possibilities on each, 5 multiple choice, 4 possibilities on each. Now, before you start actually multiplying those out, if you were going to write this in exponential, you don't have to use your calculator here. How do I express 2 times itself 10 times? 2 to the 10th. How do I express 4 times itself 5 times? 4 to the 5th. So there's your exponential form. Done. Now, base 10, you could actually go ahead and plug this in your calculator. Base 10 is like the actual expanded number. So you do 2 to the 10th, you do 4 to the 5th, and you multiply. Your graphing calculator, you could just plug that in, and it's going to give it to you. Comes out to 1,048,576. So that's the actual number. These two numbers are the same. One's an exponential, one's in base 10, but these represent the same number. And now let's put that number into scientific notation. So when we write something in scientific, the first number that we express has to be between 1 and 10. So we can only have one digit in front of my decimal. So it's 1 point, and we're not going to round this. We're going to write this all the way out. 0.48576 times 10 to the something. The exponent represents, when we're talking about powers of 10, how many actual places that the decimal is moved. The decimal was here, so it moved 3, and it moved 6. It moved 6 places, and if you actually plug this into your calculator, 1.048576 times 10 to the 6th, you're going to get back to your base 10 number. So these are 3 different ways to represent the same exact number. So now let's answer the question. If you guessed on every single question on this test, complete guess, had no idea, what's the probability that you get all of them correct? So the only way you get 100% is if you guess every single one right. So there's only one possible way to get 100%. If you change the way you guess, and you got 100% the first time, you're not going to get 100% the second time. There's only one possible way to get 100%. So it's a 1 out of, and how many different possibilities are there for the way you could have guessed this number? 1,048,576. So if you guessed on every single question, the chance of you getting 100% is 1 in a million, and actually more than a million. All right, example number 4 is pretty much the same question, just with some little things changed. So I encourage you to pause the video and try it. And then once you've got your answers, run the video and see how you did. So example number 4, we've got 5 true or false questions. So again, true or false. They have 2 options. And then we've got our multiple choice, which again, in this specific problem, they'd have to tell you, but there's 4 options. Probably A, B, C, and D. 15 of those. How many different sets of answers are possible? We're going to write them in exponential, base 10, and scientific. So just like we just did. So first of all, you're going to have 5 true or false questions, and each one of those has 2 possibilities. 1, 2, 3, 4, 5. And then you have 15 multiple choice. So each one of those has 4. So I need 15 4s. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Squeeze it in there. And so if I want to write this now in exponential, this number, it's 2 to the how many? 5th. And it's 4 to the 15th. You can plug that in your calculator and you can get your base 10. The actual number. $34,359,738,370. And then scientific. And usually in scientific, we don't write out the whole number. We round it because the whole point of scientific is to shorten this up so it's not such a big number, so many digits. But if you want to be exact, you need all of them. Decimal always comes after the first one so that this number represents something between 1 and 10. So 3 point somethings between 1 and 10. And then the power of 10 that you choose has to tell you how many decimal places you moved it. So 3, 6, 9, one more to get between the 3 and the 4, 10 spots. So if you guessed on every question, what's the probability you get them all correct? Only one possible way to get 100%. So it is 1 out of your total number of possibilities. 34,359,738,370. So your odds of getting 100%, guessing on every single one of those questions, not so good.